Hello students, today we will discuss displacement thickness, momentum thickness and energy thickness of a boundary layer theory. So let's start. So let's define displacement thickness. Displacement thickness is defined as the distance measured perpendicular to the boundary of the solid body by which boundary should be displaced to compensate for the reduction in flow rate on the account of boundary layer formation. So when a liquid come in contact with the solid surface, as you know, it will form a boundary layer like this. And this boundary layer is basically three-dimensional in diagram. When you observe from the top, you will get, so this boundary, it will be like this. So from the top, this body, stationary body is like this. So when a free stream moves in this direction, it will pass over this. So here, this is the situation. This situation is, suppose it can be written like this way in a different color. So this is the situation, and here we are considering one boundary layer like this. So this one. Now you know mass flow rate is rho u into area. Rho u into area. So this is density, this is velocity into area. This is mass flow rate. So here density is constant. You cannot change the u here actually. You cannot change the u. But only you can change in area. But again in the area you cannot change this width. Width will be constant. So, to compensate the reduction in the rate of flow of rate, reduction in the flow of rate due to this boundary layer, to compensate that, we have to shift something. So this, if you shift this is your breadth, this one your breadth, this is your height. If you shift this portion, then area will reduce. If area reduce, then we can compensate. So what is the meaning of that? Before formation of the boundary layer, this is suppose rate of flow of mass. Due to the boundary layer, due to the difference, due to the change in velocity due to viscosity here, what happened? Your reduction in flow rate occurs. To compensate that, here you have to shift this solid body. Those are actually imaginary, and if you do that, you will get the area will be reduced, and finally you get the result. Now let's try to derive the equation for displacement thickness. So here we consider unit width Meaning is this distance is suppose 1, and mass flow rate through the elementary strip. So here we consider one elementary strip, thickness dx at a distance y from this boundary. So it will be given by rho u du, small u. Then mass flow rate if plate were not there, then situation will be rho, it is capital U d. Okay, then you have to find out the reduction of mass flow rate through the elementary strip. So it will be given by rho capital U small u dy. That is for the small strip. Now total reduction of mass flow due to introduction of the plate, this plate in the bound, from where you get the boundary layer actually, it will be by delta rho u small u del u. So I already discussed about here actually. We have to displace a little bit in height, you have to reduce. So here let the plate is displaced by a distance delta star. If it is displaced by delta star, then loss of mass flow per second, mass flow rate actually is given by rho capital U delta this, and this equation must be equal. So your rho capital U delta dash must be equal to integration 0 to delta. Why it is 0 to delta? Because this from here it is delta, this is 0, so this is why it is 0 to delta. Rho capital U du, and from this equation you will derive that displacement thickness is given by this equation. One small u capital U del u. Displacement thickness. If there is a displacement thickness due to reduction in the mass flow rate, there definitely a momentum thickness also occurs. So this is defined as a distance measured perpendicular to the boundary of the solid body by which the boundary should be displaced to compensate for the reduction in momentum of the flowing fluid on the account of boundary layer formation. So similarly, we are considering one small strip here. Now we are considering for the momentum. So mass flow per second through the elementary strip if is given by rho u. We are considering with S1 unity. Now momentum per second. Momentum per second is given by, this is your mass flow rate into velocity, this is mass into velocity, so it will be rho u square del u. Similarly, momentum per second of the same mass of fluid before entering the boundary layer is given by, this is your mass and the velocity is free stream velocity, so it will be like this. So loss of momentum per second is given by small u, capital U, du, u square, or you can write capital U, small u, del u. So total loss of momentum per second. This is for the strip. For the whole it will be 0 to delta. So up to this point is delta, as you know. So it will be like this, rho u, capital U, del u. Let theta be the distance by which plate is displaced due to momentum loss. So then loss of momentum per second of a fluid through the distance theta with a velocity, that is the mainstream velocity capital U, is given by rho theta capital U square. So now these two will be equal. So rho theta capital U square U, rho U capital U small u del y, and from this you will get theta is equal to integration 0 to delta small u capital U 1 minus small u capital U del u. So this is the momentum thickness of a boundary layer. So let's come to energy thickness. It is defined as the distance measured perpendicular to the boundary of the solid body by which boundaries should be displaced to compensate for the reduction in kinetic energy of the flowing fluid on account of boundary layer formation. So similarly we consider the same thing. So at first we find out the mass of the flow per second in the elementary strip, as usual is given by rho small u del y. So if you find out the kinetic energy of this fluid, inside boundary layer, so it will be half of mu square, so it will be half rho u del u and small u square. So similarly kinetic energy of the same mass before entering the boundary layer, is given by half of this same, it will be same k square. So loss of kinetic energy through the elementary strip is given by half of rho u del u capital U square minus half of small u del u small u square. So it will be half of rho u capital U square small u square del y, and total loss of kinetic energy is given by delta integration of delta 0 to delta half of rho small u capital U square small u square del u. Now suppose delta star be the distance by which the plate is displaced to compensate for the reduction of kinetic energy. Then loss of kinetic energy is given by half of rho capital U, that's the square. Now these two will be equal. So half of small capital U star capital U square is equal to integration 0 to delta half of rho small u capital U square small u square del U. After that you will get this double star delta double star is equal to integration of 0 to delta small u divided by capital U 1 small u square capital U square del U. So this will be equal, this to this will be equal, so ultimately you will get this. So this is the derivation for energy thickness, and theta is a momentum thickness. It is given by this small u capital U 1 u small u del y, and similarly displacement thickness is given by theta 1 u capital U del U. So these are the three thicknesses: displacement thickness, momentum thickness, energy section, and this is the derivation. I hope you understand. Thank you. See you soon.